Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Cenozoic Earth history, focusing on the Paleogene and Neogene. So before we go any further, let's just get the code word out of the way. The code word for this presentation is turtle. I repeat, turtle. That's T-U-R-T-L-E. One more time, that's turtle. So please make sure you write that down, put it somewhere safe because you'll need it for the code word quiz. So what we're going to do now is we're going to discuss the geologic history of some of the other areas of North America during the Cenozoic. So we're going to focus on the interior, the Atlantic coast and the Gulf Coast primarily. Now, in terms of the continental interior, we know that by the Paleogene, the Cenozoic Sea, that's also referred to sometimes as the Cretaceous Interior Seaway, was nearly fully regressed. So if you remember, the Cretaceous Quaternary Seaway in the Cretaceous essentially bisected North America, so it cut it completely in two, and it ran approximately along this path here, which we can see behind this picture as the orange area, which essentially is the location of the Great Plains of the interior of North America. So we know that a portion of the Cenozoic Sea was still around in the North Dakota region. However, pretty much the entire lot had retreated by the Paleogene. Now, we know that sediments from the eroding Laramide highlands located to the west were transported into what was left of the Cenozoic Sea and deposited into the marine basin. Okay. However, as I said, the Cenozoic Sea was in regression, so the basin wasn't really around for that long, to be fair. Now, once the Cenozoic Sea had fully regressed, this is in the Middle Paleogene, all the other sedimentary deposits in the Great Plain region essentially are going to occur in a continental setting, and by far and away the most common continental setting are going to be fluvial sediment. So we're going to have river systems cutting across the Great Plains here, spreading sediment around all over the place. And of course, that sediment's going to be sourced from the erosion of the Rocky Mountains, and that sediment is going to be transported across the Great Plains, and it's going to primarily move down here towards the Gulf Coast. So the only local source of sediment within the Great Plains region was the Black Hills. So when I say local, I mean proximal. So when I'm talking about the erosion of the Rockies, that's a distal source of sediment. In terms of sources of sediment located in the Great Plains region, only really the Black Hills of South Dakota could possibly act as a major sediment source. And so the Black Hills are the result of early Paleogene uplift in the South Dakota area, and this uplift was a distal effect of the larger Laramide orogeny. And what it did is it went and pushed up a sequence of Precambrian granites, essentially through a sequence of younger Mesozoic and Paleozoic rocks. So the area was initially subtropical forests. However, the Great Plains as a whole has been replaced with grasslands as the climate has become more arid, and this is a general reflection of decreasing global temperatures. So as we've discussed, as we went through the Cenozoic, we've had this steady decrease in global temperature. And so this means initially, during the very early Cenozoic, areas like the Great Plains would have been quite warm and quite wet, and so there would have been excellent conditions for tropical or subtropical forests. But as the conditions started to get a bit colder and drier, we see these forests dying back, and they're replaced primarily with grassland. So now we're going to move over to the east coast, and we're going to think about the central lowlands and the Appalachian Mountains. So the formation of the Appalachian Mountains is a story of both convergent and divergent tectonism from the Precambrian all the way through to the Mesozoic. So we know that the east coast, essentially during the Paleozoic, obviously underwent the Taconic, Akkadian, the Achetan and the Alleghanian orogenies. All of those four combined are called the Appalachian orogeny. And then we know in the Triassic the area underwent rifting to create the North Atlantic Basin. Now, by the Cenozoic, this region essentially had calmed down. Everything was nice and quiet, nothing particularly spectacular was going on. Now, we know by the end of the Cretaceous that the Appalachian Mountains had been nearly completely eroded away. So if you remember, the Appalachian Mountains, which stopped forming, very, very late Permian to very early Triassic, were a Himalayan-sized mountain range, and they were almost completely eroded away by the end of the Cretaceous. And so this means that the area which we now call the modern-day Appalachians was essentially just a big, flat, low topography plain, a little bit like the area around Houston in Texas. And we know that cutting across this big flat plain, we had large meandering rivers. So obviously we then have a bit of a problem. So if we look at the picture of the Appalachians behind the text here, you can quite clearly see that it's an area which is very, very rich in topography. But that obviously doesn't work with what I've just told you. So the question is, well, where does this modern undulating topography come from? So there are two preferred models that explain why the topography changed from this plain which we had in the very late Mesozoic to a more undulating topography. So the two preferred models are, number one, it was something to do with climatic change. So what we think is there could have been a shift in climate, and this increased rates of erosion, probably mostly due to increased rainfall. Now this means that softer layers of rock will erode faster, because obviously the softer your rock is, the more easily eroded it will be. The harder your rock is, the more difficult it will be to erode. And so this means that over an extended period of time, the action of weathering will preferentially erode away the soft layers faster than the hard layers, and so the soft layers of rock will essentially begin to form topographic lows, and these topographic lows will then be exploited by rivers, and the rivers will then accentuate these topographic lows, forming valleys. Now, the fact that the Appalachian region is so heavily folded means that it's full of these nice big anticlines and synclines. So this means the same layer of rock is going to reappear at the surface several times. And so this means if that layer of rock happens to be a soft layer of rock which is easily eroded, it means on several occasions, every time it outcrops, it's going to be actively eroded quite quickly compared to other rocks, and it's going to naturally form topographic lows. And so that's the first possibility. The change that we see could just be due to erosion which is induced by climate change. The other possible option is that the area is actually being actively uplifted, so the ground's being pushed up, and this is leading to the change in topography. So during the Cenozoic, we see the Appalachian mountain belt underwent a period of uplift. So we know that there's definitely been something that's pushed the Appalachians upwards, and this has resulted in rivers cutting down quickly, creating quite steep valleys. And these rivers, of course, as mentioned already, will preferentially exploit weaker layers of rock because it's just, once again, the easiest path. It's the path of least resistance. So the question becomes, well, we know there's been some uplift, so why has that uplift occurred? Now, this is actually a bit of a tough one. There's no obvious reason to explain it. I'm just going to be honest right now. So the possible options are, number one, mantle forcing. And this simply means that underneath the modern-day Appalachians, there's a mantle convection cell, and that mantle convection cell is bringing hot mantle rocks up, and these hot mantle rocks are naturally buoyant, so they're rising up underneath the modern Appalachian region, and those buoyant hot mantle rocks are just pushing up the Appalachian region, leading to the uplift. So that's possible option number one. Option number two is that it could be something to do with the Farallon plate. So the Farallon plate, although it was subducted under the west coast of North America, it was subducting in an easterly direction. So that means it was diving down, and eventually, deep down in the mantle, it will make it essentially directly under the area which is underlain by the modern-day Appalachian region. And so it's possible that the descent of the Farallon plate could have caused some kind of mantle disturbance, and this mantle disturbance could have led to some kind of mantle upwelling underneath the Appalachians. So once again, it could have caused a region of hot mantle to rise up underneath the Appalachians, and once again, the buoyancy of this hot mantle is going to push up the Appalachian region, leading to the topography that we see. The final option is delamination, which we've already touched on. So in the case of delamination, the possibility is that at the bottom of the continental lithosphere under the modern-day Appalachian hills fell off. And so this means that the lithosphere underneath the Appalachian suddenly became thinner, it became lighter, and so this is literally going to cause it to bounce up. We're going to have an isostatic change produced by the fact the crust is suddenly a lot thinner than it was. And so this action of bouncing up could possibly have been sufficient to explain the uplift that we see. So we know that some uplift has occurred. We're not really sure why, but we also know that there were climatic changes going from the Cenozoic, going from the Cretaceous, into the Cenozoic, and so it's probably a combined factor of the climate change and the uplift, which leads to the topography which we see in the modern-day Appalachian region. So this diagram sums up what was going on. So by the late Triassic, we obviously had our mountains. By the Cretaceous, the entire area had been eroded flat. By the late Cretaceous to early Cenozoic, the area essentially is a large flat floodplain. And then, of course, we have the topography reappearing, which is probably due to a mixture of climate change and uplift. So now let's think about the southern and eastern coastal margins of North America. So the erosion of the Rocky Mountains and the Appalachian Mountains during the Cenozoic produced massive quantities of detrital sediment. So material that was eroded from the eastern slopes of the Rockies and the western slopes of the Appalachians entered a stream network that eventually emptied into, along the Gulf coastal plain. So we have material being eroded off the eastern side of the Rockies, western side of the Appalachian Highlands, and all of that material is entering the central plains of North America, and it's being transported across those plains by large rivers, and those large rivers on the whole empty out into or along the Gulf Coast plain. And so a lot of the sediment's going to be dumped down here along the northern margin of the Gulf of Mexico. So material eroded from the eastern and southern portions of the Appalachian Highlands are deposited essentially along the Atlantic coastline. So the two coastal plains, the Atlantic coastline and the Gulf Coast, essentially form a continuous belt that stretches from Massachusetts all the way down to southern Texas. So both of the areas, the Gulf Coast region and the Atlantic plains, consist of a sequence of horizontally to gently dipping seaward beds representing fluvial deposits. So we see a transition across the plain, starting with continental fluvial sediments, then going into intermediate sediments, so typically beach deposits, and then those deposits grade into marine sandstones, marine mudstones, and finally marine carbonates. So the seaward side of this sedimentary sequence lies the coastal plain sequence, which consists of beach deposits, sands, mudstones, and carbonates. So essentially, what we're seeing here when we look at the Gulf Coast regions and when we're looking at the Atlantic coastline, what we see is an area which consists of continental deposits, so river deposits, fluvial deposits, which will grade into beach deposits. The beach deposits then grade into marine sandstones grade into marine mudstones, and marine mudstones grade into the carbonates. And this is a classic passive continental margin sequence, and so this is telling us that during the Cenozoic, the Gulf Coast and the Atlantic coast were passive continental margins. Now, if we continue out into deeper water, especially in the Gulf of Mexico, we're going to enter a region which represents the continental slope. And at the bottom of the continental slope, obviously, we have the continental rise. And we know that the continental rise consists of overlapping fans which are produced by turbidite deposits. So we're going to see rocks like greywackies and mudstones. So if we look at the Gulf of Mexico here, what we can see is this coastline here, essentially the edge of this brown area, marks the coastline at the end of the Cretaceous. So what we can see here in the dark purple, these are sediments that were being deposited during the Cretaceous on the continental shelf. Then as we move into this light purple here, these are sediments which are being deposited in the Paleogene, so the early Cenozoic, once again on the continental shelf. Then we move out into this red, orange, brown color here. These are sediments being deposited in the Neogene, so essentially middle Cenozoic. Once again, we can see we're moving away. We then have the Quaternary sediments marked out here in this kind of dashed orange colour. So these are modern sedimentary deposits. Then we move out into this yellow band here. These are shelf deposits. And then we move out into this blue area here. So this represents essentially the continental slope. And then down here we have the Sigsbee Deep area, which represents essentially the abyssal plain of the Gulf of Mexico, the very, very deep marine environment. And so what we can see is that as we've progressed from the Cretaceous coastline to the modern day coastline, essentially we've been building out in a generally southerly direction. You can see this build out occurring over time. It's wonderfully clear when you look at the geologic maps. So in terms of the Atlantic continental margin, during the late Triassic, obviously we know this margin was an active rift. However, once rifting had finished, it became a passive continental margin. So the Mesozoic rifting and Cenozoic uplift of the Appalachian Mountains produced a number of sedimentary basins along the Atlantic margin, and these were filled with sediments that were being eroded from the Appalachian highlands during the Mesozoic and the Cenozoic. So sediments on the Atlantic coastal plain occur as seaward, so that's eastward, thickening wedges. So we see sedimentary sequences coming off the Atlantic plain. They are thinnest, closest to the coastline, and they get thicker as you move out into deeper water. And so these wedges essentially represent a graded transition from terrestrial sediments at the thin end of the wedge to marine sediments at the thicker end of the wedge. So finally, we're just going to drop back onto the Gulf Coast region. So following the regression of the Xenioperic Sea at the end of the Cretaceous, there was a final marine transgression that occurred in the late Paleocene and Eocene epochs. So this is the Tehesoperic Sea. And this particular Peric Sea was, compared to the others at least, tiny. So it was a relatively small Peric Sea, and it was pretty brief. It wasn't around for very long. At its maximum extent, it was restricted to the Atlantic and Gulf coastal plains, although it did also encroach on some areas of California, not many. The furthest it managed to move inland was the area which is now marked out by the Mississippi, Arkansas, Tennessee junction. So you can see here it is. So you can see we have the Atlantic plain here, Florida here, and the Gulf Coast plain here, which are inundated. We can see that this area here represents the maximum extent of the Peric Sea, reaching this Mississippi, Arkansas, Texas junction right here. So you can see it wasn't a particularly extensive body of water. So the sedimentation pattern for the Gulf Coast was established in the Cretaceous and continues until the present day. Essentially, it's an area which is dominated by continental marine sediments. So the sediments that are eroded from the eastern Laramides, western Appalachians, essentially are transported across the Great Plains and central lowlands, and they're deposited in continental, transitional, and marine environments, depending on where the rivers drop them. So this deposition once again produces one of these seaward thickening wedges. So if we look at the sedimentary sequences associated with the Gulf Coast, once again we have a triangular shaped body of sediment. It's thinnest closest to the coast, and it gets thicker as you move out into the marine environment. And once again, this is a standard passive continental feature. We tend to see a lot of these seaward thickening sedimentary sequences associated with passive continental margins. So the sedimentary facies development that we see in these wedges of marine sediments that are being deposited from the Cretaceous onwards are controlled by the regression of the Tehesoperic Sea. So as part of this Epiric event, we actually have 8 minor transgressive regressive cycles, which we can see in the sedimentary sequence. And so this means obviously the facies are going to be shifting depending on whether the ocean is transgressing or regressing. And so this means the sediments associated with the Tejas sequence essentially show quite strong intertonguing as the facies were moving due to sea level changes. In terms of the majority of the sediment being deposited as part of the Tehesoperic Sea, most of it was detrital, and it was coming from the erosion of the Rockies and the western side of the Appalachian Highlands. However, the area which we now call Florida went and formed a major carbonate platform. So in that area you had nice clear warm water, there wasn't a lot of detrital sediment coming into that area, and so it was essentially the perfect conditions for the development of carbonates. And so we see the Florida area essentially as a carbonate producing shelf from the Cretaceous through the vast majority of the Cenozoic, and there are still some regions of it now which are still actively producing large quantities of carbonate. The classic example would be the Florida Keys. Okay everybody, so that's it for Cenozoic Earth history for the Paleogene and Neogene. So thank you for watching the presentation and have a good day.